In the last lectures, we have seen many different properties for the Lebesgue integral on abstract measure spaces. In this lecture, we will go back to our initial space, which was the Euclidean space Rd with our favorite Lebesgue measure, and we will see that there are some more interesting properties that hold in this special case. But let me recall first what we have seen so far for abstract measure spaces. So for abstract measure space, we have seen, of course, we have seen the basic properties of the Lebesgue integral, basic properties of measurable functions and Lebesgue integral. We have also seen the abstract Egorov's theorem in the abstract setting, which was based on the Littlewood's third principle, which was that a sequence of measurable functions converges uniformly outside a set of negligible measure. And we have also seen various convergence theorems. So here we have seen monotone convergence theorem, Fatou's lemma, and the dominated convergence theorem, which are the three main pillars of Lebesgue's integration theory. So these all hold for the abstract measure space setting. Now let's come back to Littlewood's three principles that we have seen before. So the first one was that every measurable set is almost open. Every measurable set is almost open. This was the definition of our notion of Lebesgue measurability for sets in Rd. And we also had that every measurable set with finite measure is almost a finite union of boxes. So I left it as an exercise, which is not very difficult to show, that if you have a set of finite measure, then you can approximate it with a finite union of boxes. So this was the Littlewood's first principle, and we have already seen this part. We have also seen Littlewood's third principle, which says that every pointwise convergence sequence of measurable functions is almost uniformly convergent. So this was, of course, Egorov's theorem, which gave for any sequence of measurable functions converging pointwise to another function on a set of finite measure, then we can extract a set of negligible measure outside of which the convergence was uniform. So this was the Littlewood's third principle. What we haven't seen yet is Littlewood's second principle. So this we haven't seen, the second principle, which says that every L1 function or absolutely integrable function is almost continuous. Now note that we cannot state this second principle for arbitrary measure spaces, because we need the notion of continuity, which only holds for topological spaces. And so this second principle we will state for the Euclidean space Rd. One can also state it for more general topological spaces like locally compact Hausdorff spaces, but we won't see it here, and we will only state it for Rd. So this is what's called Lusin's theorem. And we will see this in today's lecture. But first, I will like to go back to Egorov's theorem and state a slightly more strengthened version of Egorov's theorem when we are dealing with the Euclidean space with the Lebesgue measure. So for this, let me make a couple of definitions. So let me define the notion of local uniform convergence of functions. Local uniform convergence in RD. Okay, so we are back to the case of the Euclidean space with the Lebesgue measure. Okay, so here we consider the measure space RD with the sigma algebra of Lebesgue measurable sets and the Lebesgue measure. So let's define what is local uniform convergence for such a for RD. So a sequence of measurable functions, complex measurable functions Fn is said to converge locally uniformly to a measurable function f on RD, again with values in the complex numbers, if Fn converges to f uniformly on every bounded subset E of RD. So rather than asking for uniform convergence on the entirety of RD, we only ask it for having uniform convergence on every bounded subset of RD. So let's see an example of a sequence of functions converging locally uniformly but not uniformly. So first example is if you take Fn, so let me take on R, if you take Fn to be the function x over n, okay, n greater than equal to 1, then Fn converges to the function 0 locally uniformly but not uniformly. So we see that this is a weaker notion of convergence, and I leave it to you as an exercise to check that this convergence is not uniform but it is locally uniform. Similarly, if you take again on R, if you take the function fx to be the exponential function and write it as the limit of the partial sums of its Taylor series k equal to 1 to 0 to n, and you take x to the power n over x to the power k, over k factorial. Then if you define these as your f and x, then this convergence is locally uniform but not uniform. So this convergence is locally uniform but not uniform. So there are many interesting cases of functions, sequences of functions converging locally uniformly but not uniformly. So let me state a version of Egorov's theorem which uses the notion of local uniform convergence in RD and which slightly strengthens our abstract Egorov's theorem. So let's look at the statement of Egorov's theorem for RD. So it states that if Fn is a sequence of complex measurable functions on RD and it converges pointwise to some function f, pointwise almost everywhere in RD. So here we allow convergence pointwise almost everywhere. Then given epsilon greater than 0, there exists a set f such that the measure of this set is less than or equal to epsilon, and Fn converges to f locally uniformly on the complement of f, which is the same as saying that Fn converges uniformly on Fn f complement intersection some bounded set E for every bounded set E in RD. So let me write another equivalent statement, which is that Fn converges to f uniformly on f complement intersection B0 M0 for all positive integers M0. So we can check that this last statement is actually equivalent to the middle statement, which was for every bounded subset of E, but this is for closed Euclidean balls. So this is the closed Euclidean balls of radius M0 and center 0. So we will prove this last statement to establish Egorov's theorem. So let's look at the proof, but first let me recall what was the abstract version of Egorov's theorem. So in this case we had that if Fn converges to f pointwise, so we did not assume pointwise almost everywhere, but we only assumed pointwise convergence on a measurable set E such that it has finite measure, then for any epsilon greater than 0 there exists a subset A epsilon of E such that the measure of E minus A epsilon is less than or equal to epsilon, and Fn converges to f uniformly on this set A epsilon. So outside this set A epsilon, which has negligible measure inside E, we have uniform convergence on A epsilon itself. So we are going to use this abstract version. So for Fn converging to f in RD, for any positive integer m, we take E to be B0m in this above abstract version of Egorov's theorem. Then given epsilon greater than 0, there exists a set A m epsilon, a subset of B0m, such that first that the measure of B0m minus A m epsilon is less than or equal to epsilon, and secondly that Fn converges to f uniformly on A m epsilon. So we can apply for any m this abstract Egorov's theorem, and we deduce this statement. So here I would like to take, rather than epsilon, I would like to take epsilon over 2 to the power m, so that I can use an summation trick as we have done before. So now let us denote by Fm epsilon this set B0m minus Am epsilon, and we take F to be the union of all these Fm epsilons. Then of course the measure of F is less than or equal to the sum of all the Fm epsilons, m greater than or equal to 1, and so this is less than or equal to epsilon because each one is less than or equal to epsilon over 2 to the power m. So we have that this measure of this set F is less than or equal to epsilon, and now I claim that for any m naught Fn converges to F uniformly on F complement intersection B0 m naught. So let's see why this is true. So we have that B0 m naught intersection F complement is the same as B0 m naught intersection with, so the complement of F. So we had F itself is a union of these Fm epsilons, and so you have to take the complement. So this is B0 m naught intersection with the intersection now of m greater than or equal to 1 F the complement of Fm epsilon, but the complement of Fm epsilon, the intersection is just the same. This intersection is the same as the intersection of all Am epsilon. So remember that Am epsilon was the set we chose inside each B0m, the closed unit ball B0m, and our F epsilon was precisely this set B0m minus Am epsilon. So the complement of Fm epsilon is, so let me write it down here, Fm epsilon complement is equal to B0m intersection Am epsilon complement, and then you have a complement. So then you get B0m complement union Am epsilon. So if you take the intersection of all these, so if you take the intersection over all m, here also intersection over all m, and here also intersection over all m, then the first part intersection m greater than or equal to 1 B0m complement, this is nothing but Rd, so you don't get anything extra here, and you will only get the intersection of Am epsilon. So this is why we can write this last statement that B0 m naught intersection F complement is the same as B0 m naught intersection with the intersection of all Am epsilons. But now this set is a subset of B0 m naught intersection Am naught epsilon in particular, because we have an intersection over all m, and this is nothing but Am naught epsilon because this is a subset, Am naught epsilon is a subset of B0 m naught by construction. So on Am naught epsilon we have by construction that Fn converges to F uniformly, and so this implies that Fn converges to F uniformly on B0 m naught intersection F complement, since it converges uniformly on Am naught epsilon. So we see that we have local uniform convergence in RD when you have a sequence of functions converging pointwise almost everywhere. So here I missed one thing, which is that our functions converges pointwise everywhere, pointwise almost everywhere. Here we have pointwise almost everywhere convergence, but here we need pointwise everywhere convergence. But this is not an issue because we can modify this pointwise convergence such that it converges everywhere, and the modification is on a set of measure 0, and then we can add this set to our set F at the end, so that we still have a set of measure less than or equal to epsilon. So note that if Fn converges to F pointwise almost everywhere, then after modification on a set, let's call it E, of measure 0, without loss of generality we can assume that Fn converges to F pointwise everywhere rather than almost everywhere, and in the end we can take the union of F union this set of measure 0, and this set still has measure less than or equal to epsilon. So modifications on a set of measure 0 doesn't affect our statement of Egorov's theorem.